Okay, now we are moving to the next topic, application of your Kohlrausch's law. I think Kohlrausch's law and the related ideas or the problems which we are already discussed in the previous class. Fine. So we are moving to the next application of Kohlrausch's law. The very first application, that is to find limiting molar conductivity or limiting conductivity, whatever it may be, molar conductivity or equivalent conductivity. We can find the limiting molar or limiting equivalent conductivity, simply limiting conductivity of a weak electrolyte. Limiting conductivity of a weak electrolyte. We can very easily find the limiting conductivity of a weak electrolyte. That is the first application. Ready? Okay. So let's check how we can find that. And I can explain through a question or more than one questions. Listen here. It is given that the limiting molar conductivity of NaCl is X. Let it be X. And the limiting molar conductivity of NH4Cl be Y. Ready? Okay. And limiting molar conductivity of sodium hydroxide NaOH be Z. And these are little bit strong electrolytes, right? NaCl, NH4Cl, NaOH, like that. Okay. Now, you are asked to find the limiting molar conductivity of the weak electrolyte ammonium hydroxide. The weak electrolyte ammonium hydroxide. How we can find it? It is very easy. It is very easy. This is the question. So we know that we want to find the limiting molar conductivity of ammonium hydroxide, a weak electrolyte, right? Yeah. So it is clear that according to Kohlrausch's law, this limiting molar conductivity will be the limiting molar conductivity of NH4 plus limiting molar conductivity of OH minus, because these all are monatomic, which means they all can form mono ions. Na plus Cl minus, NH4 plus Cl minus, Na plus OH minus, like that. Okay, they all forms monatomic ions. Ready? Now listen. So we actually require this one, right? Yeah. This one and this one from the above question. And it is clear that what about the molar conductivity of lambda M0 of NaCl according to Kohlrausch's law? Lambda M0 Na plus lambda M0 Cl minus. And what about NH4Cl? Lambda M0 NH4 plus lambda M0 Cl minus. What about NaOH? Lambda M0 Na plus lambda M0 OH minus. So listen here. What we need actually? We need lambda M NH4 plus, right? And lambda M OH minus. So where is your lambda M NH4 plus? It is in the second equation, right? Yeah. The lambda M NH4 plus is in the second equation. Whereas lambda M0 OH minus, that is in the third equation. So it is clear that we want to add lambda M0 of NH4 plus and lambda M0 of OH minus. So we want to add these two, right? Yeah. But when you are adding these two indirectly or alternately, lambda M0 of Na plus and lambda M0 Cl minus also get added, right? Yeah. So we actually no need of that. Okay, we don't want that. the addition of lambda m0 of NO plus and Cl minus. We simply require this addition, right? Yeah. So this is an extra addition, and that extra addition we can solve it by subtracting by lambda m0 of Na plus and lambda m0 of Cl minus, right? Yeah. So this extra added term, we can easily remove it by subtracting with the first one. So that is the procedure we have to do. What? Let it be the equation number 1, 2, 3. So simply add 2 and 3, right? Yeah. So simply you can add 2 and 3. So we got the required one, and the alternate addition can be subtracted using the another equation, which means the first equation. So this addition can be compensated by this one, by subtracting this one. So you can add 2 plus 3 and subtract the 1 from that. Okay, fine. So now it is showing simply the values become y plus az minus x. This will be the lambda m0 of NH power plus. Okay, it is very easy, I think. By simply by have a look itself, we can simply choose the value, right? Because we need NH4 and OH. Well, the NH4 is in this equation and OH is in this equation. So simply add that. Ready? And so therefore this one may get added. You can subtract it by using first one. Using a simple logic itself, you can easily find it, right? Yeah. So I'll give you one more question. That is, the question is, lambda m0 of sodium acetate is T. Lambda m0 of HCl is HCl is U. Lambda m0 of NaCl is V. And you can find the lambda m0 of HAC. And HAC is a weak electrolyte. Ready? How can we find that? It is very clear that we have to add the two equations from that, and moreover, we want to subtract one from it, right? Yeah. So what do you mean by AC? AC stands that acetate ion. AC stands for acetate ion. Acetate ion means CH3COO minus. So the CH3COO minus is simply said to be AC. So this is HAC, HCH3COO, which means acetic acid. And this is NaAC, NaCH3COO, which means sodium acetate. Anyway, by having a look itself, we can find the value, right? Yeah. Here we need H from as a cation and AC as an anion. So where is H plus as a cation from these three equations? Here, right? So our required H plus is in the second equation. So we want to simply put the second equation, no doubt. Ready? And the required anion AC minus is in the first equation. So we want to club these two, right? Yes. So U plus T. But when we are clubbing these two, the additional term which get added is NaCl. So we can subtract it by using the remaining equation. So this will be the answer, right? Okay. I think this is okay for you. And this is a simple type which is described in your NCERT textbook, okay? The question may be a little bit complex, which means because these all kind of components are monovalent, right? And you know that an electrolyte may not be 1:1 type. It may be 1:2 or 1:3 like that, okay? So this here the all electrolyte is in a 1:1 type. 1:1 type means a cation, a anion, like that, okay? But it may be 1:2 or 1:3 like that. Okay, so for that kind of electrolyte, how can we do the, or how can we find the molar conductivity? That is the question. Listen here. If molar conductivity of Ca3PO4 twice is X, calcium phosphate, and this is a 3:2 type electrolyte, and molar conductivity of CaCl2 is Y, and this is a 1:2 type. Okay, and molar conductivity of AlCl3 is equal to Z. Okay. Find the molar conductivity of AlPO4, aluminum phosphate. Aluminum phosphate is not a weak electrolyte, but you can find it in the exactly same way as that of your previous question. But there is one difficulty. What is that difficulty means? We actually required, what about the decomposition of aluminum phosphate? Al3 plus plus PO4 minus. What about Al3 plus AlCl3? Al3 plus plus 3Cl minus. What about CaCl2? Ca2 plus plus 2Cl minus. What about Ca3PO4 twice? 3Ca2 plus plus 2PO4 minus. Ready, fine. So we actually need lambda m0 of Al3 plus plus lambda m0 of PO4 minus. Ready? But when you are considering this other equation, it is actually lambda m0 of Al3 plus lambda m0 of 3 into lambda m0 of Cl minus. What about here? Lambda m0 of Ca2 plus lambda m0 of Cl minus into 2. Here, lambda m0 of Ca2 plus into 3 plus lambda m0 of PO4 minus into 2. So it is very difficult to find lambda m0 of Al3 plus and lambda m0 of PO4 minus from this equation, because this is not a simple equation, have some kind of multiple here, right? Yeah. So the method which is used in the previous case is not well applicable here. So in this section or in this type of question, how it can be solved means you simply find the equivalent conductivity. You simply find the equivalent conductivity of each electrolyte. Equivalent conductivity of each electrolyte. What is the difference between equivalent conductivity and molar conductivity? In molar conductivity, the number of cations and number of anions will be there. But in equivalent conductivity, we can simply write the cation and anion, right? So that will be more easy. So here in terms of equivalent conductivity, it will be lambda equivalent. This is molar conductivity, right? Yeah. So what is the relation between molar conductivity of Ca3PO4 twice and equivalent conductivity of CO3PO4 twice? We know that there is a relation which is in which is in contact with the n factor, right? Okay. If you have molar conductivity and you want to find equivalent conductivity, what is the relation? The equivalent conductivity may obtain by dividing the molar conductivity by n factor, right? Yeah. So what is n factor here? Total number of positive or negative charge, 6. What is n factor here? That is 2. I know how to calculate. I think you know that how to calculate the n factor, right? And what is the equivalent conductivity here? 3. Fine. So here we have molar conductivity, right? So this method is not working here, or it may take more time. Okay. So molar conductivity of Ca3PO4 twice is given. We can easily find the equivalent conductivity. So equivalent conductivity of Ca3PO4 twice. What will be the expression? Equivalent conductivity of that cation plus simply plus is enough, right? No need of multiplying with 3 because you know the difference between molar conductivity and equivalent conductivity. Moreover, equivalent conductivity of P of 3 minus. Okay, and this value not equal to x. This value not equal to x. The x is the molar conductivity, right? Yeah, x is the molar conductivity of calcium phosphate, but we return the equivalent conductivity, right? So equivalent conductivity is the molar conductivity divided by n factor. The molar conductivity is x and n factor is 6. So equivalent conductivity will be x by 6. Molar conductivity x and n factor is 6. So equivalent conductivity of that corresponding salt is x by 6. Fine. What about the next one? Equivalent conductivity of CaCl2. Equivalent conductivity of CaCl2. Equivalent conductivity of CaCl2 is equivalent conductivity of Ca2 plus equivalent conductivity of Cl minus. Ready? And this will be equal to the molar conductivity divided by n factor. The molar conductivity is given in the question as y, where the n factor we know that it is 2. So this is y by 2. Once again, the third one, equivalent conductivity of, tell me, equivalent conductivity of what? AlCl3. So lambda E AlCl3, which is equal to lambda E Al3 plus lambda E Cl minus. And this will be equal to the molar conductivity divided by n factor, where the molar conductivity is Z, and n factor we know that it is 3. Okay. So these all are equivalent conductivity, right? So from this equation, we can easily find the equivalent conductivity of asked one or the question. Equivalent conductivity of the unknown, right? So from these three equations, let me find the equivalent conductivity of required one, Al3PO4. That is equivalent conductivity of Al3 plus equivalent conductivity of PO4 minus. Ready? And it is very easily find from this one, right? So PO4 minus here and Al3 plus here. So these two equations have to add, so that Cl minus and Ca2 plus also get added, which can be subtracted using the second equation. Okay, so it is very clear that 1 and 3 added and 2 subtracted. So what will be the nature? 1 and 3 added means x by 6 plus z by 3, and subtracted category is y by 2. So this is the equivalent conductivity of Al3PO4 twice, but we actually require the molar conductivity. We know that molar conductivity of Al3PO4 thrice, or sorry, Al3PO4 is its equivalent conductivity into n factor. What is its equivalent conductivity? X by 6 plus z by 3 minus y by 2, all of n factor. What is n factor? It is 3. Yeah. So x by 2 plus z minus 3y by 2. This will be the molar conductivity of that particular vector, right? Okay. So question may ask like this also. Okay. So if your calculation or if your terms are a little bit complex, it is very easy to calculate in terms of equivalent conductance. Okay. I'll give you one more model, then it will be okay for you. And I think we want to discuss the very same pattern of question in your discussion material. Let us check. Okay. So I'll give you one more. Listen. Lambda M0 of barium, no need of barium. Sodium nitride is A, and lambda M0 of sodium chloride is B. Lambda M0 of Ca3N2, calcium nitride, is C. Find lambda M0 of CaCl2. Okay. So what do you want to do that? You find the lambda 0 of sodium nitride. First you find the n factor. N factor here is 3. Total procedure. N factor here is 1. N factor here is 6. N factor here is 2. This is the first step. Then you convert the lambda M0 into lambda E0. Sodium nitride will be equal to lambda 0. Simply you choose the cation Na plus, lambda 0, N3 minus. And this value will be not equal to A because A is its molar conductivity. Then if the molar conductivity is A for your sodium nitride, then what is equivalent conductivity? That molar conductivity divided by n factor, that is 3. Okay, like here also, lambda 0 of NaCl, lambda 0 Na plus plus, lambda 0 Cl minus, and it will be equal to B divided by 1 because the n factor is 1. Like lambda 0 of Ca3N2. Tell me, lambda 0 Ca2 plus plus, lambda 0 N3 minus. Then that will be equal to C divided by 6. Ready? Okay. Fine. And we know that lambda M0 of CaCl2 is equal to lambda 0 of CaCl2 into the n factor. So first you find the lambda 0 of CaCl2. Lambda 0 of CaCl2 means lambda 0 of Ca2 plus plus lambda 0 of Cl minus. That can be very easily found from this equation. Okay, ready? The required categories are Ca2 plus and Cl minus. So add this one. And the excess Na3 can be replaced by this one. Fine? So B by 1 plus C by 6. From that, A by 3 can be subtracted. So you obtain what? Lambda 0 of CaCl2. But actually we need lambda M0 of CaCl2, which is equal to lambda 0 of CaCl2 is B by 1 plus C by 6 minus A by 3. All of multiplied with the n factor is 6, right? N factor is 6, so into 6. So 6B plus C minus 2A is the answer. Ready? Fine. Okay. Okay. So the first application is over. Ready? Moving to the second application. To find degree of ionization. What? Degree of ionization of weak electrolyte. Degree of ionization, you know, alpha. Alpha equal to number of species ionized divided by total. So, there alpha, which is equal to, what do you mean by alpha? Number of species ionized divided by total species for ionization. how much electrolyte you are given for ionization, that is the denominator, and from that how much is ionized, that is the numerator, and this value will be numerically equal to lambda m divided by lambda m0, lambda m divided by lambda n0, or this value will be equal to lambda e divided by lambda e0, and that is a expression. What do you mean by lambda m? Lambda m is the molar conductivity at any concentration, and lambda m0 is the molar conductivity at zero concentration or limiting molar conductivity. How can we find the lambda m? It is already discussed. 1000 times of kappa divided by molarity. And what is lambda e? Equivalent conductivity at any concentration. How can we find the equivalent conductivity? 1000 kappa divided by normality. Ready? Fine. So this is a second application to find the degree of ionization of a weak electrolyte. Ready? Moving to the third application. So you simply if you are asked to find the degree of ionization of a particular electrolyte in a particular concentration, first of all you should able to find the limit molar conductivity at that concentration or equivalent conductivity at that concentration. Take it in the numerator. Ready? And divide it by using its equivalent conductivity, limiting equivalent conductivity or limiting molar conductivity. Then the ratio will be exactly equal to the alpha. That is experimentally observed. Ready? Third one, if you have alpha value, we can easily find the dissociation constant, right? Yeah. To find the ionization constant, dissociation constant or ionization constant. Ionization constant of weak electrolyte. Find the ionization constant of a weak electrolyte. Once you people have alpha value, take the square of alpha and multiply with the concentration and divided with the 1 minus alpha, then you obtain degree of ionization constant, where K is the ionization constant and it is not equal to the conductivity kappa. The K is ionization constant, but this K is specific conductance. What is this one? Specific conductance. And this is pronounced as kappa, and this is simply K. Okay. Ready? Where C is a particular concentration. We already told you that. Ionization constant or alpha, which can be measured in a particular concentration, that molarity or normality, that is actually here C. Ready? And we can substitute alpha by lambda m by lambda 0. Then what will be the expression for your K? Let's check. Put alpha equal to lambda by lambda 0. Lambda by lambda 0. Whatever it may be, m or e. Simply lambda by lambda 0. What will be the equation? K equal to C into lambda by lambda 0 square divided by 1 minus lambda by lambda 0. By crossing the denominator, what will be the equation? C into lambda square by lambda 0 square divided by lambda 0 minus lambda divided by lambda 0. This lambda 0 square is cancelled, and this one will be here. So C lambda square divided by lambda 0 of lambda 0 minus lambda will be the equation. So what will be the equation for K? K will be C into lambda 0 square divided by C into lambda square divided by lambda 0 of lambda 0 minus lambda. And this is important. If it is in terms of molar conductivity, C lambda m square divided by lambda m0 of lambda m0 minus lambda 0. lambda m0 of lambda m0 minus lambda m. If it is in terms of, if your lambda is smaller conductivity, then the K will be C lambda m square divided by lambda m0 of lambda m0 minus lambda m. Or if your lambda is equivalent conductivity, lambda is equivalent conductivity, if lambda is equivalent conductivity, then the equation will be K equal to C into lambda E square divided by lambda E0 of lambda E0 minus lambda E. Okay, so that depends on the case. You can choose the equation, and this is a general format. Ready? So if you have the degree of ionization alpha, you can easily find the ionization constant of a weak electrolyte. Ready? Fine. So these are the next two applications. Ready? So the first section is over. The section is conductivity. So let's have to discuss more and more problems from that. Okay, fine. So now we can discuss problems from your discussion material regarding the first section, conductivity.